All right, back to integration. All right, here's how I'm gonna finish off this capacitor problem. We're going to move into the induction coil, integrals involving the induction coil, some applications of the induction coil, so I will probably get through this either today and finish it on Wednesday, and then Wednesday we move into a concept called differential equations, which is basically describing dynamical systems, it's just, again, we're going to look at it as we're going to show you a tool. We don't have to worry about deriving everything. That'll come later down the road. But right now we're just going to show you the tool. Here's some of the techniques on how to use the tool to solve engineering problems. So we'll go from there, okay? Any questions on the homeworks or anything yet? Everybody okay? All right. Here what we're going to do is we're going to have a current source that's located on the left-hand side here is going to be charging and discharging that capacitor. Whoops, let me go back. So the current source, now we have 1, 2, 1, 2, 3, 4. We got 4 different time intervals where this current is changing. All right? Here we're going to be charging it up. Over here we're going to be discharging it. Here we're not going to be doing anything to it. And then up here we're going to charge it up again. Okay? All right? Okay. You had that befuddled look, my man. All right, so now what we need to do is you need to break the, again, how do we look at the problem? We have 4, 1, 2, 3, there's 4 different time intervals which this waveform is changing. It's an alternating current, okay? So now what we're going to do is we're going to start off with the first time interval. And again, this capacitor has an initial voltage on it of 10 volts and it's 4 millifarad. So what we're going to start off with, which is 0 is less than t, which is less than 2. So we're going to solve the problem only concerning ourselves with this first time interval right here. We will take the baby steps on it, all right? So that's what we're going to do. Constant current going into that capacitor, it's going to do something. It's going to charge up. It actually has a 10-volt initial charge on it. So now we know that since we're going to work with this time interval, I of t is equal to 15 milliamps, okay, over that time interval. So it's constant, 15 milliamps, and we know that V at t equal to 0 is equal to 10 volts. So we have it, it already has an initial charge on it, okay? All right, so now we set it up. We know that the voltage, the capacitor voltage V of t, oh, you need it written bigger, right? Bigger? Bigger. Bigger. Well, you know what? Let me do this. This goes, maybe we will use the middle one. All right, so I'm just going to make a little note for myself. It goes here, 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 here. And this was what? This is 15 milliamps. This is minus 10 milliamps. And then that looks like, what's that last one go to? That looks like 10, yeah. So this one comes across to 10. Let's push this up. And let me do. We'll do that. Is that okay? Everybody all right? No! Up. Stop. There. Good. All right. All right, so I'll work right to left, okay? All right, so now, what's this thing? All right, so now we know that the voltage V of t is going to equal 1 over c, the integral of I of t dt. Now, and it's plus V at 0, okay? So now we have to put on the limits of integration here are from 0 to 2, okay? Or 0 to 2. Or I'm just going to, let's make this t for the moment here. I'm going to make this t. This upper limit's going to be t, where t is going to take on the interval from 0 to 2. So now we have V of t is going to equal 1 over c, which is 1 over 4 times 10 to the minus 3 integral from 0 to t. Now, 15 milliamps. 15 times 10 to the minus 3 dt plus 10. All right, so that's what we're integrating out now. So I'm going to bring this out in front. V of t is equal to 15 times 10 to the minus 3 divided by 4 times 10 to the minus 3. The integral from 0 to t of dt plus 10. Okay? Everybody with me? All right? Yeah. The 15 comes from... This thing has a mind of its own. Stop! You've got to be smarter than the projector screen. You know what I mean? I'm trying to... The 15 comes from that 15 milliamps up at the top. All right? It took me a while to answer your question again. All right?
So from like, if it was to say like from like 0 to 2, like we would just look at the graph from what's 0 to 2.
Right. That's what we're saying. We're breaking it up into the baby steps. So the 15 came from that 15 milliamps right there. Right there. So now we just have the integral of dt. All right? And if you look in your, go back to these integrations, the integral of dt from 0 to t is equal to t itself. Okay? All right? So what we're going to have is, so we can cancel out the 10 to the minus 3s. We're going to have v of t is going to equal 15 over 4 times t evaluated on the limits between 0 and t plus 10. Okay? So now I just plug in, this is going to give me 15 over 4 times t minus 0, that's evaluating this thing, plus 10, which is equal to 15 over 4t plus 10. That's what that guy's going to be. Yes, ma'am.
So you put three instead of two. So
Yes.
if you didn't substitute between, you just had like from 0 to 2. What would it be?
Okay, well here, so the final result that we have now is for 0 less than t, which is less than or equal to 2, all right, we have that the solution is v of t is equal to 15 over 4t plus 10. That's my solution for that time interval.
Okay.
And you always, this has to go with this, because this expression is only valid over that time period.
Okay. So if I wanted to figure out what it was at 2, I would have plugged in 2.
You plug in t equals 2.
Okay.
And we're going to have to do that. Because notice that the solution for the integration of a capacitor, the solution is v of t is equal to 1 over c, the integral from 0 to t, I of t dt plus t0. Now, we're now going to have, this could actually be this. This is t0, and this is t0. So now what I have to do is I have to apply this formula for my next time interval, and I have to calculate what the thing is going to be at t equals 2. So now we're going to go 0 is less than, oh no, we're not on 0 here. What was the next time interval? Anybody? 2 to 4. Was it 2 to 4? All right, so now for 2 is less than or equal to t, which is less than or equal to 4, again, v of t is equal to the integral 1 over c, the integral from t0 to t of I of t dt plus v at t0. That's what that integral is. Now we plug in, what is the number for t0? What's t0? 2. Just plug in 2 here. So now we're going to have v of t is equal to 1 over c, which is 1 over 4 times 10 to the minus 3. The integral now goes from 2 to t. And what was the value? I think it was minus 10 times 10 to the minus 3 dt plus v at t equals 2. How do we get v at t equals 2?
Oh, wait, what? I'm sorry.
Oh, you're right. I know. You're trying to do 3 different things. Listen to me, write, and think. Dangerous. All right? It's hard to do. See, when I get in that situation, all 3 neurons start fighting each other. All right? It's a real battle up here, man. Okay? Yeah.
Where's the -10?
That's from the current graph. From 2 to 4. From the current graph. Morning. Afternoon. All right, so now what we do, we have to find this value at t equals 2 from this expression right here. From right here. So now I put in t equals 2 here, what am I going to get? T equals 2. So putting it in, what? 34 plus 10. So I need somebody give me a quick calculation. All right, so this is going to be v of t is equal to minus 10 times 10 to the minus 3 divided by 4 times 10 to the minus 3. Integral from 2 to t of dt plus, what do you get? 17.5. All right, now again, we have to evaluate our integral. V of t is equal to, now I'm going to have minus 10 over 4, and I'm going to have the dt comes out to be t evaluated from 2 to t plus 17.5. All right? So then now I substitute in for what the limits of integration. Minus 10 fourths. This gives me t minus 2 plus 17.5. So now we have v of t. Let's multiply everything out. V of t is going to equal minus 10 over 4t. Then I'm going to have minus a minus, so that's going to give me 20/4, which looks like it's going to give me plus 20 over 4 plus 17.5. So therefore, v of t is minus 10 over 4t. 20/4 is 5, so this looks like it gives me 22.5. Okay? Yeah. When you I'm evaluating. This is my integration, right? And then I have to evaluate it between the upper limit minus the lower limit. So the upper limit is t, the lower limit is this. Does that make sense? So see, what I like about this problem is it forces you to understand what these time intervals are. You see what I'm saying? Over here, when we integrated it out between 0 and t, it was t minus 0. Here, it's I'm evaluating this integral from the lower limit, which is 2, to the upper limit, which is t. So this becomes t minus 2. We're good. All right.
So for the first integral, when it was 0 to 2, and the 0 just like canceled out.
The 0 just watched itself out right here.
Right, so you didn't have to redo like especially this one, but you had to plug in 4, and you had to plug in 2, and then subtract those 2.
Yeah.
Okay.
Well, now here, this solution, again, just as we had for the other problem, this solution is valid over what? 2, yeah. 2 is less than or equal to t, which is less than or equal to 4. That's what that's valid over.
Okay.
Make sense? All right, now, now we go to the next one. V at t. Now this will be valid for 4 is less than or equal to t, which is less than or equal to 6. Now if you look at your thing, so that's going to equal 1 over c, and in this case, I of t is equal to 0. Okay? For that interval, you with me? All right, so now what I do is I substitute in 1 over c, which is 1 over, what was it, 4 times 10 to the minus 3. The integral now, the lower limit is 4. The upper limit is t, where t is going to vary up to 6. What's the value of the current on this time interval? 0. Plus v at t equals 4. Okay? So therefore, I don't even have to worry about this integral because I'm integrating 0. The area under 0 is what? A big goose egg, baby. 0. All right? 0. So therefore, this I don't even have to worry about. That's gone. What's v at t equals 4? I get it from back here. So substitute in, so v at t equals 4 is equal to minus 10 times the 4 divided by the 4 plus 22.5, which looks like it's equal to 12.5. So therefore, on the interval 4 is less than or equal to t, which is less than or equal to 6, v t is equal to 12.5. It's constant. It is constant. Okle dokle. All right, now we go for the last one. This is now pops back up to 10 milliamps. So for 0 is less than or, I'm sorry, 0. 6 is less than t, which is less than or equal to 8. I of t is equal to plus 10 milliamps. So now we have v of t is 1 over c. The integral from 6 to 8 of 10 times 10 to the minus 3 dt. Oh, and that I'll just leave that upper limit on the integration. Instead of 8, I'll just put it as t, because I'll get the time function out of it. T plus v at t equals 6. Okay? And what's v at t equals 6? 12.5. This is equal to 12.5. So now, bringing that 10 to the times 10 to the minus 3 outside. So now I just have the integral from 6 to 8 of dt plus 12.5. All right, again, the 10 to the minus 3's are canceling, so I have 10 over 4. The integral of dt, I'm sorry, again, this is t. That's t. So this is 10 over 4, and I have this, the integral is t evaluated between 6 and t plus 12.5. And then we have here v of t is equal to 10 over 4 times t minus 6 plus 12.5. So V of t is equal to, we're going to have 10 over 4t minus 60 over 4 plus 12.5. And that is valid for 6 is less than or equal to t, which is less than or equal to 8. So that's how we broke up those each one of those intervals into the little baby steps here. There we go. It looks like every time I send something to projector, it automatically. I didn't design it. I'm just a user. So again, we broke it up for 4 time intervals. 0 to 2. There we go. Now when we went for the next time interval, we set up the integral expression, and then the only thing now is we have to worry about v at t0 for this time interval. We cranked it out, and we got it. We went for the next time interval. Again, you have to worry about these v at t, the initial charges on a capacitor. All right? Okay? Yeah.
Your answer, why did you plug 4 into that equation instead of the
Here? Because I'm plugging in. All right. I had to find from this expression here. See, all right, are you okay with me here? Are we all right up there? So now I have to find v at t equals 4. So I get it, previous one over here. So I plug in minus 10 over 4 times 4 plus 22.5 gives me 12.5.
So I'm saying you couldn't plug it into that one?
No, because this one's only valid for what? 0 to 2. I have to use again, that's what I like about this problem. I have to use the solution from the previous time interval to give me the initial condition on the capacitor for the next time interval. So here's what we had to do. Let me just draw it for you. Again, we had 2, 4, 6, and 8 was the final one. Here, we solved this one. I think it goes up like this. And then, in order for this, I needed to know what v at t equals 2 was for the interval from 2 to 4. And I think it went down, or something like that. It goes down like that. And then, here, at this point, I needed v. You see what I'm saying? And that's where these numbers are coming in. See, the first through, t0 was what? It was 0, and we knew it was 10. So we plugged it in there. So that gave me the solution from 0 to 2. Then I'm going to use expression I have to evaluate that expression, this guy here, at t equals 2. That's where I get my 17.5. But the interval I'm solving is for 2 is less than t, which is less than 4. Does that clear it up? Anybody? Yeah.
For the second to last step, where you're subtracting we know t, don't we?
We do. Oh, yeah.
So why can't we just plug it in now?
Here's how this integral works, all right? This integral here, that's the one that we've been using, right? But instead of 0, it's t0. So here, the integral from t0 to t of dt evaluated on the interval from the lower limit to the upper limit, which is equal to t minus t0. Is that clear it up? Yeah. See, again, in integrations, you have to worry about the lower limit and the upper limit. And you evaluate the function at the upper limit minus evaluating the function at the lower limit. In this case, it would be, the function was just t by itself. All right? Okay? All right. So now we can take a look. Just to summarize what we did. So here we did, summarizing. I have 1 over c, integral of the current plus the initial voltage. Here's the initial voltage, just cranking out this integral. And for that current was 15 milliamps over that time interval. We set it up, and we get, this is what we get, all right? So that number, 15 force, is 3.76, okay? So that's valid over that time interval. Then, now we need V at 2. This is what you were asking earlier. We need V at 2 for the next time interval. So we go up to the next time interval. So V at 2 is 17.5. We then put it in. Again, V at 2. The current one is minus 10 milliamps. We crank it out, so we get 22.5 plus 2.5t. Now I'm going to need, for the time interval, from I'm going to need V at 4, because I'm now going to work on the interval from 4 to 6. The current is 0. I need V at 4, and it's 12.5 from the previous interval. Then I go for 8. We're up to 10 milliamps. 2.5, t minus 6. That's where we got the minus 6 that you were asking about when I substitute everything in. So here is my complete solution. Time interval 1, time interval 2, time interval 3, time interval 4, and then I graph each of those functions. All right? They're all linear functions. Because what I'm doing is I know they're all linear functions, because what are we integrating each time? What was the current each one? It was a constant, right? 15, minus 10, 0, 10. Anytime you integrate a constant, what do you get? A linear curve. Depending upon if that constant is positive, you're going to get a curve with a positive slope. If the curve is negative, you're going to get it with a negative slope. So I could have looked, actually I could have looked at, if I go back, from that graph there, I could have just said, you know what, before I get into all the crazy mathematics, let's take a look at what's going to happen. You guys can't see that. Let me, whee! Since I know that this current the current does that, I can then say pretty much that since I have an initial capacitor voltage that is positive, when I integrate this plus 15, this was minus 10, when I integrate this, is it going to give me a slope that is positive or negative? It's got to give me a positive slope. So I know it's going to look something like this over that time interval. Now I'm going to integrate something that is negative. That's going to give me a linear curve with what kind of slope? Negative. It's got to be negative. So the curve's got to look something like this. All right, going down. I don't know what this, whatever. Now I'm integrating 0. What's the curve look like? It's flat. It's constant. It's going to go like this. Now I'm integrating a positive number. What is it going to do? It's got to go like that. So even before I start the problem with all the, the numbers and integrals and all that stuff, I can sketch out and say, you know what, my result better look something like that. It's got to. And I know here, in a physical sense, what's happening? The capacitor is charging. This interval, what's the capacitor doing? This interval, what's the capacitor doing? And This interval, what's it doing? Charging back up again. It's a nice problem where you got to think it through. Okay, all these little time interval stuff. All right. Okay, make sense? Everybody good? All right, let's see. That was we do it this guy. All right. All right. We're done with capacitance. What I'll do is we're going to do inductance for the next 20 minutes or so. Wednesday, I will finish off the inductance stuff. I'll go over some homework problems out of Chapter 9, some of the circuit stuff. And then starting that following Monday, we'll get into some most honorable differential equations. I had Dr. Wu for differential equations. Wooski, I call him. He said, Mr. Halford, you're dangerous. Said, we have ways to make you learn these things. Yes. All right, so the inductor came out of, guys putting around with electricity and stuff, and we call it inductor because what you have is basically a wire with a current through it induces a magnetic field. That's why we call it an inductor. Okay, that's where the thing came from. So you can have metal objects do some pretty neat things with an inductor. And again, you just run a current near a compass, and you'll see that compass needle will start to shift. And there indeed is a magnetic field around there. All right. So then, in order to make the magnetic field strong, we simply wrap it into a coil. Hence the term induction coil. It's a coil. All right. Typically, some have an iron core in it to constrict the magnetic field even more. And then it has a number of turns on it. It's a passive element. It's not like a battery. It is an energy storage element. We can, just like the capacitor, energy storage element. Because now, instead of using a voltage for the capacitor, we're now doing, that stores it in an electric field, we're now using current and a magnetic field. And they come in all different shapes and sizes. There's all kinds of them. These are all sitting in your little laptops. These were early transformers that you had. Primary side, secondary side. This was Faraday's original ring. Primary side over here, secondary side over here. And then you can get these. These are used in all your audio systems, stuff like that. These little, this is what we call a step-down transformer. You're taking a high voltage and bringing it down to a low voltage. This is Joseph Henry. He was the first guy that actually started doing mechanical work. He had the big thing here. He had this lever arm sitting here. And as he turned the current on and off in the system, he'll be able to pick up heavy objects down here. So the lever arm would go up, down, based upon what the current was going on here. And here, you guys, if you go down past Yonk Avenue, heading towards the airport, just take a look over where those salvage yards are. You'll see them all over the place, picking up scrap metal. All right, these are huge induction coils that are in there. You could actually, some of the first ones were doorbells. Here's an induction coil sitting in here, and what we do is, as I run a current through here, this lever arm gets pulled into the coil. That gets pulled into the coil there. Well, the little hammer up here hits the gong. So it goes bing. Now, at that point, the contact breaks down here and the current goes off. And there's a little spring in here to pull that arm back. So it goes ding. But if I keep my finger on the doorbell, the current's going to make a contact again here, and it's going to go bang, opens the circuit up, closes it, bang, open the circuit up, no current, bang. So that's how, and if you do that real quickly, you'll hear your doorbell. All right. For those of you that are gearheads, this is the solenoid in your starter engine that's in your car. Okay, that's it. You have a heavy-duty leads are all the way back. Now you're talking major current here. Stuff that'll do you in a hurry. All right, you're up in the amps here. You've got a mounting bracket that sits up here. You got a little spring sitting in here. This is a plunger, And in here, we have a big coil that's wrapped around the inside of this guy. What happens is, as you energize over here, this plunger gets shot out. It gets physically shot out into the starter, and then it'll hit it. And then the battery is now connected in the circuit, and then the starter will start starting your engine. As soon as it's done, this spring pulls the plunger back. So as you turn your key on, that plunger is engaged, sticking out. No, that's not the best picture of it. Sorry, it's so grainy. But here's the battery. I'll fix this slide for you on the web. But here is the solenoid. Here's my starter motor. When you turn that key to the right, this plunger then, boom, goes up to these two contact points. Those contact points then bring the battery in parallel with the starter, and you're drawing current out of the battery into the starter, which is now going to rotate the starter, which is going to get your engine started. Okay? You can generate, now this is, the nice thing about this is how hydroelectric plants and everything work. You can generate electricity by having a coil of wire, and this is a bar magnet sitting in here, and if you ram that, if I have the coil of wire and I start doing this with the magnet, a current gets induced into that coil of wire. So a time-varying magnetic field induces a current into a wire. That generates electricity. That's exactly how a hydroelectric plant works. I have a big cylinder. I put these two big magnets on it. My feet are now sitting where the turbines are, where you're letting the water in, and I just start doing this. And then I get up to high speeds. And as I bring those magnets past the coils of wire that are on the outside of the containment vessel, as they go by, you've got a time-varying magnetic field that is inducing a current in all those coils. You generate electricity, all right? I told you the DC-AC one, right? Yeah. Oh, what happened to the drummer for DC-AC? Anybody hear about that one? Anybody know the drummer for DC-AC? Anybody know what DC-AC is? AC/DC. All right. Did I turn this on? I didn't mean to say that. No, you hear what happened to the drummer? He hired a hitman in New Zealand to kill 2 people. Don't piss off the... They dropped the charges, by the way, over the weekend. He didn't... And if you notice on the new AC/DC album, his picture isn't even on it. Ooh. Piss somebody off. All right, yeah, so you can generate electricity with these hydro plants. And basically they work because you would have a plant, you then go through what's called a step-up transformer. Again, 2 induction coils in close proximity to each other. One has a real high number of turns on the secondary side, low number of turns on the primary side. So that takes the voltage here and steps it way up. You then transmit that down your transmission system all the way down to, you get to a substation. You can see these all over. And then from the substation, you can then drive it into an industrial plant, or I can also transmit it down further. And if you look outside telephone poles, you'll see that those are step-down transformers that bring everything down to 110. Okay, 15 amps. Okay, so that's another application of induction coils. And this is what these generators. I think this was Edison's original one. Here's a guy standing right there. These things were massive. I mean, they were big. You know, big turbines that were going on there, big dynamos that were happening there. So basically, the way that this induction coil works is you have a primary side and a secondary side. The number of turns here is less than the number of turns here. So what happens is you're now going to step the voltage up. So if this is like 10 volts here, you can step this up to 100, whatever. It depends on the number of turns, whatever that turns ratio is. You can think of this transformer. Everybody ride a bike? You got gears on it, right? It's the same thing. If you put it in low, you're going to be spinning a lot because you're using the low gear down here. This gear up here remains. Sometimes you have 2 of them on the top and usually 5 down here. Depends on how many speeds you have. But a transformer it's the electrical analogy of a bike with gears. Same thing. Stepping up and stepping down gear ratios. I'm stepping up and stepping down turn ratios here. And as we saw the early telegraph, and you'll notice the early telegraph, they always ran the wires next to trains. Because if something broke, you jumped on the train and you went out and fixed the wire. I mean, we weren't out there just running wires all over the place. So typically they were right next to train, and the guys that were in the train stations were actually running the telegraphs. And then I showed you, I think I showed you this video? Yeah, you saw that video. And then also, they call him the father of the telegraph. Bull! He didn't invent it. All he did was invent the code. That's Morse's code. So that was his claim to fame. And what these guys did was obviously they had all kinds of iron magnets and stuff back there, and they could make needles move and point towards letters, and there's all different types of stuff. But it came down to a communication system that now can go across the Atlantic, across continents. So now I can have a communication system instantaneous, traveling at the speed of light. Traveling at the speed of light. All right. Oh, anybody play electric guitar? Yeah. There's a great Nova. You ever hear a Nova series on PBS? They have a great, I think I have the video somewhere. And here's some interesting problems. I mean, you're talking at this time, the 1830s, 1840s and stuff like that. They would make sections of wire, and then they would splice it together on the boats. So you would have a couple of ships with you, and they just drop the cables down. Drop the cables down. Interesting. And then literally, it was in North Jersey or Cape Cod. The other one was in Ireland. They literally had rooms filled with lead-acid batteries to run these real high currents. Because again, resistance is a function of length. So you're running that cable a couple thousand miles. You got a lot of resistance to go through. All right. The other problem that they had was all of a sudden they got it working, it would stop. And here you, how am I going to go back and figure out what was happening is, anybody know how a shark attacks its prey? When a shark goes to attack you, or whatever, the sea otter or whatever, it always closes its eyes to protect its eyes. You know, because you got arms, claws that are flashing around. So now the question is, how does the shark get you? We give off, every muscle in our body has current running through it. Well, current running through a piece of something gives off what?
Magnetic field.
A magnetic field. It has thousands of sensors in the front of its nose that can detect small changes in electromagnetic fields. So when it's coming out to get you, it's gone blind. So the problem was now you're running cables at the bottom of the ocean, and what's going through those cables? A current, which is creating what? A magnetic field. And what's the shark want to do? It wants to bite the freaking magnetic field. They were pulling up the cables, and you saw big teeth sharks, big teeth marks in the cables. So then they had to insulate them a lot better. But this is a true story. I mean, it's, you know, I wouldn't. You encase in a metal itself inside. The field never gets. It's a Faraday shield, we call it. So you encase it in there. Yeah. But it's interesting. Even scuba divers now, scuba divers that are like going to wrecks and stuff like that, they sit there. You'll see a little antenna coming off the back of their tanks. They see a shark coming around. You'll see them hit a button. What they're doing is charging up a capacitor. So they charge up this capacitor, and if the shark gets real close, they discharge it through the wire, and the shark freaks out. Now you're hitting it with a big electromagnetic pulse. And it takes off. It doesn't like that big boom, you know. Anybody play guitar? Electric? And what's on there? Strings and what else? What are the pickups? You're guessing now, but they are. They're coils. These pickups that you have down here are coils. And you got metal strings here. So effectively what you're doing is pluck that metal string. Now metal has a little magnetic field around it, right? So now what I'm doing is, here I have a coil down here. I'm plucking these strings. And what's happening is I got a little wire sitting in here, and this goes off to my thing. As I start plucking these strings, a magnetic field changes here. I have a coil of wire near that magnetic field. What's going to get induced into that coil of wire? A current. That current's then going to come out. And that current's going to mimic the movement of that string. And that's what you have. The string at rest, it's not going to pick anything up because there's no moving magnetic field. I then pluck it this way, I'll get a current that's going this way, left to right. I pluck it the other way, it's going to get a current moving this way. And that current is going right out, but it's got the same signature as that vibrating steel string. So that's my spiel, all right? Let me just show you. Got 5 minutes left. All right. Yeah. All right, so this is the symbol for an induction coil. The relationship is the voltage across an induction coil is equal to the inductance itself in henries times the rate of change of current as a function of time. This is the analogy of capacitance. These problems are going to be very similar to ones you saw with capacitance. So therefore, we have the current through a coil itself. We solve that equation for the inductor current 1 over L, the integral from T0 to T, V of T plus I at T0. The last, for the capacitor, if you notice, this was V of T is 1 over T, the integral from T0 to T of I of T dt plus V at T0. So it's just the opposite. Just you're replacing the inductance with the capacitance. And the power is just 1/2 times the inductance times the current through the inductance squared. All right? And let me show you a quick video.
Were you able to find the one where you welded?
No, it's on that tape that got eaten up in here, and I got to fix it. But here what we have, did I show you this one? Oh, all right. This is where the thing was floating in the thin air? Yep. All right, well, here, I'll show you how to make a very simple DC motor. Whoops. Hang tight, we got 3 minutes left, gang. All right, let me just show you. What we have here is I have a coil of wire that is being held up by 2 contact points, and then I have a D-cell battery in here, all right? And there's a little magnet sitting on the top. So there's a little magnet right there. Can now make a motor. All right, have a good one, gang. I'll see you Wednesday.